Tonight, you're going to learn a truth that directly contradicts what your eyes tell you. Look at the night sky. Stars everywhere. Galaxies swirling in cosmic spirals. Everything seems full, dense, alive with light. But when scientists measure reality at the largest scales, they discover something terrifying. Matter is almost impossibly rare. The space between galaxies is growing faster every moment, and the forces tearing the universe apart are only getting stronger. By the end of this video, you will understand why the universe is empty, and why that emptiness is growing. What dark matter and dark energy actually do. Why this exact moment in cosmic history is fragile in ways most people never consider. And you may never look at the night sky the same way again. Stand far enough from the city on a clear night, and you'll see thousands of stars. The Milky Way stretches across the sky like a river of light. It's beautiful, and it creates a deeply misleading impression of abundance. All that light, all those stars, surely the universe must be packed with matter. Here's the problem. Every single star you can see with your naked eye is in our immediate cosmic neighborhood. The farthest stars visible without a telescope are roughly 15,000 light-years away. That sounds far. It is far by human standards, but the Milky Way galaxy is 100,000 light-years across. You're seeing less than 15% of your own galaxy, and your galaxy is just one of several 100 billion in the observable universe. That sky full of stars is your local backyard. It's like standing in your yard and assuming the entire Earth must look just like that yard. Now point a telescope at a dark, empty patch of sky. Choose a region with absolutely nothing visible to the naked eye, just blackness. In 1995, the Hubble Space Telescope did exactly that. They pointed it at a tiny patch in the constellation Ursa Major so small that it would take 12 million such patches to cover the entire sky. The telescope stared at that spot for 10 consecutive days, gathering every photon that arrived. What did it find? Approximately 3,000 galaxies, entire galaxies packed into a region of sky the size of a grain of sand held at arm's length. Every single blob of light in that image was a galaxy containing hundreds of billions of stars. This became known as the Hubble Deep Field, and it showed astronomers something profound. Everywhere you look, even in the darkest patches of sky, there are galaxies. Billions of them. They repeated the experiment in other patches of sky. Same result. Galaxies everywhere. Distant galaxies, nearby galaxies, spiral galaxies, elliptical galaxies, irregular galaxies colliding and merging. So the universe must be full, right? All these galaxies packed into every corner. The universe must be dense with matter. But here's where we need to do the math. The observable universe contains approximately 2 trillion galaxies. Each galaxy holds somewhere between 10 million and 1 trillion stars, depending on its size. The average is roughly 100 billion. So 2 trillion galaxies times 100 billion stars gives us around 200 billion trillion stars. 2 followed by 23 zeros. That sounds like a lot. It is a lot. But now calculate how much space those stars actually occupy. A typical star like our Sun has a diameter of about 864,000 miles. Work through the geometry and multiply by 200 billion trillion stars, and you get the total volume occupied by all the stars in the observable universe. Now compare that to the volume of the observable universe itself, a sphere roughly 46.5 billion light-years in radius. When you divide one by the other, Stars occupy approximately 0.000. All the stars combined would occupy a volume smaller than a single atom. Actually smaller than that, more like a single proton. And that's just stars. Most of a star's volume is empty space too. The nucleus of an atom takes up about 1/1,000,000th of the atom's volume. So even the matter inside stars is mostly emptiness. The universe isn't just mostly empty. It is almost entirely nothing. And we haven't even talked about the space between stars within galaxies or the space between galaxies themselves. The Milky Way contains approximately 200 billion stars spread across 100,000 light years. Our nearest stellar neighbor, Proxima Centauri, is about 4.2 light years away, roughly 25 trillion miles. If you scaled the Sun down to the size of a grain of sand 1 millimeter across, the nearest star would be about 19 miles away, 30 miles of empty space between 2 grains of sand, and galaxies are separated by even more dramatic distances. The Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years away. The Milky Way is 100,000 light-years across, so the distance to Andromeda is 25 times the width of our own galaxy. 2 grains of sand separated by a football field, if we're keeping our scale. Between them, mostly nothing. Vacuum, darkness, and this is in our local group, one of the denser regions of the universe. So the universe is mostly empty space between stars, with more empty space between galaxies, with even more empty space between galaxy clusters. But we're not done, because even counting all the stars and all the galaxies and all the gas and dust between them, we're still missing most of the universe. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma Galaxy Cluster, a large group of galaxies about 320 million light-years away. Zwicky measured how fast the galaxies in the cluster were moving. He knew the cluster was held together by gravity, with all the galaxies orbiting a common center of mass. From the galaxies' speeds, he could calculate how much total mass must be present to generate enough gravity to keep them together. Then he looked at the galaxies themselves, counted them, measured their brightness, estimated their mass, and he discovered a problem. The galaxies weren't nearly massive enough. Based on visible matter, the cluster should fly apart. The galaxies were moving too fast to be held together by the gravity of visible matter alone. Zwicky calculated the cluster needed about 400 times more mass than he could see. He proposed that most of the mass must be invisible. Dark matter. Nobody believed him. It sounded absurd. Invisible matter that somehow had mass but didn't interact with light. Scientists looked for other explanations. Maybe Zwicky made a measurement error. Maybe the galaxies weren't truly gravitationally bound. Maybe our understanding of gravity was wrong at large scales. But the problem refused to go away. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies and measured how fast stars orbit the galactic center at different distances. In our solar system, planets closer to the Sun orbit faster than planets farther out. Mercury faster than Earth, Earth faster than Mars. This makes sense because gravity weakens with distance. Galaxies should work the same way. Stars near the galactic center should orbit faster than stars in the outer regions. But that's not what Rubin found. Stars in the outer regions of galaxies orbit just as fast as stars near the center, sometimes even faster. This made no sense unless there was additional mass in the outer regions providing extra gravitational pull. Mass that wasn't visible. Rubin's observations confirmed Zwicky's finding. Galaxies contain far more mass than we can see. The visible stars and gas make up only about 15% of a galaxy's total mass. The other 85% is dark matter, and it's not just galaxies. Dark matter shows up everywhere astronomers look: in galaxy clusters, in the cosmic web, in gravitational lensing measurements, in the patterns of the cosmic microwave background radiation. Every independent method of measurement points to the same conclusion. Most of the matter in the universe is invisible. We can't see it. We can't touch it. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way. But it has mass. It curves space-time. It exerts gravitational pull, and it outweighs normal matter by a factor of about 6 to 1. For every kilogram of normal matter, protons, neutrons, electrons, the stuff that makes up atoms and molecules and stars and planets and people, there are approximately 6 kilograms of dark matter. So when we calculated that stars occupy a tiny fraction of space, we were only counting normal matter. Dark matter spreads across even larger volumes, though we can't see it directly. Current estimates suggest dark matter makes up about 27% of the universe's total mass energy content. Normal matter, everything we can see and touch, makes up about 5%. That means 95% of the universe's mass energy is in forms we don't fully understand. Let's sit with that for a moment. The stuff you're made of, the stuff planets and stars are made of, the stuff that produces every photon of light we've ever detected, that is a 5% minority in this universe. Dark matter is actually what made galaxies possible in the first place. Without it, galaxies as we know them couldn't have formed at all. In the early universe, hydrogen and helium gas was spread fairly uniformly throughout space. To form galaxies, this gas needed to collapse under gravity into dense clouds. But normal matter interacts with radiation. As gas clouds collapse and heat up, they emit radiation that creates pressure, resisting further collapse. The gas wants to collapse under gravity, but radiation pressure pushes back, preventing it. Dark matter has no such problem. It doesn't interact with radiation. It doesn't emit light, doesn't absorb light, doesn't feel radiation pressure. So dark matter could collapse freely under gravity without resistance. In the early universe, dark matter formed first, clumping together into halos, spherical clouds held together by their own gravity. These dark matter halos created deep gravitational wells in the fabric of space-time. Ordinary matter, hydrogen and helium gas, fell into these wells. Once the gas was concentrated by the dark matter's gravity, it could collapse further and begin forming stars. So every galaxy has a dark matter halo surrounding it. The visible galaxy sits at the center of a much larger invisible structure. The Milky Way's visible disk is about 100,000 light-years across, but its dark matter halo extends at least 600,000 light-years, possibly farther, 6 times larger than what we can see. And the dark matter halo contains about 10 times as much mass as all the stars and gas in the visible galaxy combined. When you look at an image of the Milky Way, you're seeing less than 10% of the galaxy's total mass. Scientists have built sensitive detectors deep underground, trying to catch dark matter particles directly. The detectors are underground to shield them from cosmic rays and interference. They're looking for the rare event where a dark matter particle passes through the detector and collides with a normal atom. Such collisions should be incredibly rare, but if you have a large enough detector and wait long enough, you might detect a few. So far, nothing conclusive. Other experiments search for dark matter at particle colliders like the Large Hadron Collider, trying to create dark matter particles by smashing normal particles together at extremely high energies. If dark matter particles are created, they would fly out of the detector without leaving a trace, but their existence would be inferred from missing energy and momentum. Again, no confirmed detection. We have several theories about what dark matter might be: weakly interacting massive particles, axions, primordial black holes formed in the early universe, but none have been confirmed. This is one of the biggest unsolved mysteries in physics. We're trying to understand what constitutes 27% of the universe's mass, and we have no confirmed answer. Dark matter is passing through you right now. Billions of particles are streaming through Earth, through this building, through your body every second. You don't feel it because it doesn't interact electromagnetically. It passes through as if you aren't there. We know it exists only because of its gravitational effects on galaxies. The majority of matter in this universe is invisible, surrounding us everywhere, and we still don't know what it is. And it gets worse, because there's dark energy. In 1998, two independent teams of astronomers were studying distant supernovae. A particular type, called Type 1a, is extremely useful because it always explodes at approximately the same brightness. Here's why. A Type 1a supernova occurs in a binary star system where a white dwarf, the dense remnant of a dead star, pulls matter from a companion star. When the white dwarf reaches exactly 1.4 times the mass of our Sun, a critical threshold called the Chandrasekhar limit, carbon fusion suddenly ignites in a runaway reaction, and the entire star explodes in seconds, releasing as much energy as the Sun will emit over its entire 10 billion year lifetime. Because this always happens at the same mass, every Type 1a supernova reaches roughly the same peak brightness. They are standard candles, objects whose intrinsic brightness is known. Measure how dim one appears from Earth, and you can calculate exactly how far away it is. In the 1990s, two teams used this technique to measure the universe's expansion rate, specifically to determine how fast the expansion was slowing down. Everyone expected it to be slowing. After the Big Bang, the universe started expanding rapidly. But matter has mass. Mass creates gravity, and gravity pulls things together. So over time, gravity should be putting the brakes on. The question was whether there was enough matter to eventually halt expansion entirely and cause the universe to recollapse, or whether expansion would continue forever at an ever-decreasing rate. Both teams spent years searching for supernovae, observing them with the largest telescopes available, carefully analyzing the data, and in 1998, both announced their results independently. The distant supernovae were fainter than expected, not by a lot, but by a statistically significant, undeniable amount. Fainter means farther away, and farther away than predicted means the universe expanded more than expected. The only explanation, the expansion rate increased over time instead of decreasing. The universe's expansion is accelerating. This was completely unexpected. Many physicists initially assumed it was a systematic error, some flaw in the observations. But both teams found the same result independently. And as more supernovae were observed in the following years, the signal became stronger and clearer. The acceleration is real. Something is pushing space apart, counteracting gravity. We call it dark energy. But that's just a label for our ignorance. The simplest explanation is that dark energy is a property of space itself, that empty space has energy. This sounds strange, but it's predicted by quantum mechanics. In quantum field theory, even empty space is filled with quantum fields that permeate all of space. These fields have a ground state, a lowest possible energy level, but that ground state has a non-zero energy density. Even in a perfect vacuum, quantum fields contribute a certain amount of energy per cubic meter. This is called vacuum energy, or the cosmological constant. Einstein actually proposed a cosmological constant in 1917, not because he knew about quantum fields, but because he wanted to make the universe static. He later called it his biggest blunder, after Hubble discovered the universe is actually expanding. But now, 80 years later, observations suggest the cosmological constant might be real after all. If space has a non-zero vacuum energy density, and that density remains constant as space expands, then, as the universe grows, the total amount of vacuum energy increases. More space means more vacuum energy, and this energy has a repulsive effect, causing space to expand faster. This creates a feedback loop. Expansion creates more space creates more vacuum energy causes faster expansion. The acceleration compounds over time. There is one catastrophic problem with this explanation. When physicists calculate what the vacuum energy density should be based on quantum field theory, they get an answer roughly 10 to the power of 120 times larger than what we observe. A discrepancy of 120 orders of magnitude. The worst prediction in the history of physics. Something is either catastrophically wrong with our understanding of quantum field theory, or there's some mechanism canceling out most of the vacuum energy, leaving only a tiny residual amount. Nobody knows what that mechanism might be. Let's take full stock of where we are. Dark energy makes up approximately 68% of the universe's total mass energy content. Dark matter is about 27%. Normal matter, everything we can see, touch, and feel, is only 5%. Think about that. We live in a universe where 95% of everything is stuff we don't understand. 27% is dark matter we can't see, but know exists because of its gravitational effects. 68% is dark energy we can't see, but know exists because it's accelerating the expansion of space. Only 5% is ordinary matter. And even that 5% is spread so thin across such enormous distances that it might as well be absent in most locations. We pride ourselves on scientific understanding. We've decoded the atom, mapped the human genome, sent probes beyond the solar system, detected gravitational waves. We understand chemistry, electromagnetism, nuclear forces, quantum mechanics, relativity. But when we look at the universe as a whole, we have to admit that most of it is a mystery. We can measure dark matter's effects, but can't identify what it is. We can measure dark energy's effects, but have no accepted theory for what causes it. We're like ancient astronomers who could track the planet's motions, but didn't know planets were worlds. We can measure and predict, but we don't deeply understand. And there's yet another layer to this emptiness: cosmic voids. When astronomers map the distribution of galaxies across large volumes of space, they discover that galaxies aren't randomly distributed. They cluster together in groups. Those groups form larger structures called superclusters. And those superclusters are connected by filaments of galaxies stretching across hundreds of millions of light years. And between these filaments are voids, enormous regions where almost no galaxies exist. In the 1970s and 80s, astronomers began creating three-dimensional maps of galaxy positions. They measured not just where galaxies appear on the sky, but how far away they are, using redshift, the stretching of light caused by expansion, which shifts distant galaxies' light toward longer, redder wavelengths. The more redshifted, the farther away. By measuring redshifts for millions of galaxies, astronomers could plot their three-dimensional positions. A pattern emerged. Galaxies are arranged in an intricate web-like structure. Long filaments, flat sheets, massive clusters where filaments intersect, and between them, voids. The first large void was discovered in 1981 by Robert Kirshner and colleagues in the constellation Boötes. They expected to find galaxies distributed more or less evenly. Instead, they found a sphere roughly 330 million light-years in diameter, containing only about 60 galaxies. A typical region that size contains around 10,000 galaxies. The Boötes void has 60. That's 99.4% fewer galaxies than expected. It's not completely empty, but it's as close to empty as you can get while still being part of the observable universe. An observer on a planet in a galaxy near the center of the Boötes void would look out in every direction and see almost nothing. The nearest significant concentration of galaxies would be more than 165 million light-years away in any direction. For comparison, our nearest large galactic neighbor, Andromeda, is only 2.5 million light-years away. We are in a relatively crowded part of the universe. That void observer's night sky would be profoundly dark. No Milky Way band across the sky, no neighboring galaxies visible to the naked eye, just darkness. After the Boötes void was discovered, astronomers looked for others and found them everywhere. Voids are not rare. They are the dominant feature of the universe's large-scale structure. Most of the universe's volume is void. The giant void is about 1 billion light-years across. The Eridanus supervoid is similarly large and corresponds to a cold spot in the cosmic microwave background, a region of sky that's slightly colder than average, puzzling because it's larger and colder than theoretical models predict. Some physicists have even speculated this might be evidence of a collision between our universe and another in a multiverse, though most likely it's an unusually large void combined with statistical fluctuation. And the local void is much closer to home, only about 150 million light-years away. We're on its edge, looking in. The structure called the dipole repeller associated with this local void appears to be pushing our local group away from it. Not because the void pushes directly, but because the overdense regions surrounding the void pull matter toward them, creating an apparent repulsion from the void's center. Matter flows away from voids toward filaments and clusters. The whole structure is dynamic, flowing over hundreds of millions of years. But voids don't fill in over time. They're not temporary features that will eventually disappear. In fact, voids are growing. As the universe expands, matter in underdense regions becomes even more spread out, while matter in overdense regions becomes more concentrated. The rich get richer and the poor get poorer, cosmologically speaking. Voids expand faster than the average expansion rate because they have less matter to slow expansion locally. And dark energy accelerates this process. As expansion accelerates, voids grow even faster. So the cosmic web structure is becoming more pronounced over time. Filaments are growing denser and voids are growing emptier. Eventually, many billions of years from now, most matter in the universe will be concentrated in isolated clusters separated by enormous voids containing almost nothing. The universe is evolving toward maximum emptiness. Within voids, conditions are profoundly different from our region. We live in the local sheet, a relatively dense structure. There are dozens of galaxies within a few million light years. Star formation is ongoing in the Milky Way and other nearby galaxies. In a void, conditions are harsher. The few galaxies that exist in voids tend to be small, dim, and low in star formation, called void galaxies. They're typically dwarf galaxies containing less gas, the raw material for new stars. They're more isolated, rarely interacting with neighbors, missing the gravitational interactions that trigger star formation. Some void galaxies are among the most pristine, unchanged objects in the universe, isolated for billions of years with no major interactions or mergers, still looking similar to how they looked billions of years ago. Fossils of the early universe, quiet and unchanged. A civilization arising in a void galaxy would have a very different view of the cosmos. They would see far fewer galaxies in their sky. Their cosmology would be different. They might discover the cosmic microwave background and realize the universe had a hot, dense beginning. But they might never realize that most of the universe is arranged in filaments and clusters. They might think their lonely void was representative of the entire cosmos. It's a sobering thought. Our understanding of the universe is shaped by where we happen to be located. The existence of voids also tells us something crucial about the early universe. The pattern of filaments and voids we see today originated from tiny density fluctuations shortly after the Big Bang. Regions that were 1 part in 100,000 denser than average collapsed over billions of years into filaments and clusters. Regions that were 1 part in 100,000 less dense became voids. The structure we see today is the amplified echo of quantum fluctuations from the first moments of cosmic history. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation, space expanding faster than light, doubling in size many times over in roughly 10 to the power of minus 32 seconds. Different models predict different details, but the basic idea is that in that incomprehensibly brief moment, the universe expanded by a factor of at least 10 to the power of 26. For comparison, there are roughly 10 to the 18th power seconds in the entire age of the universe. Inflation lasted 10 to the minus 32 seconds, 1 million trillion times shorter than the universe's current age. During inflation, quantum fluctuations in the inflaton field, fluctuations smaller than a proton, were stretched to the scale of galaxies. These became the density variations in the early universe, regions slightly denser than average, regions slightly less dense. Those quantum fluctuations determined where galaxies would form, where voids would empty out, where we would end up. The structure of the entire cosmos traces back to randomness at the quantum scale. And those fluctuations had to be exactly what they were. If they had been zero, perfectly uniform, gravity would have had nothing to work with. Matter would have remained evenly spread as the universe expanded. No galaxies, no stars, no planets, no life. Just a thin gas of hydrogen and helium spreading ever thinner across expanding space. But if the density variations had been much larger, say 1 part in 1,000 instead of 1 in 100,000, gravity would have been too strong. Dense regions would have collapsed too quickly and violently, forming black holes directly instead of galaxies. The universe would have been full of black holes with no opportunity for stars or planets to form. The amplitude had to be just right, large enough for structure to form, small enough that structure forms gradually, allowing stars and galaxies instead of just black holes. This fine-tuning is part of why the universe is as empty as it is, and it's one of the deepest unsolved questions in physics. Now let's talk about where all of this is going. Space itself is expanding. It's not that galaxies are moving through space away from each other. The space between galaxies is growing. Imagine dots on the surface of a balloon being inflated. The dots move apart not because they're traveling across the surface, but because the surface itself is stretching. Every point is moving away from every other point. There's no center to the expansion on the surface. The universe works the same way, but in 3 dimensions. And the farther apart 2 objects are, the faster they appear to recede, because there's more space between them to stretch. This is Hubble's law, discovered by Edwin Hubble in 1929. He found a linear relationship. Galaxies twice as far away were receding twice as fast. Galaxies 3 times farther away were receding 3 times as fast. The only explanation was that the universe itself is expanding. Space is growing, carrying galaxies apart. The rate of expansion is described by the Hubble constant. Current measurements put it at approximately 43.5 miles per second per megaparsec, where a megaparsec is roughly 3.3 million light-years. So for every 3.3 million light-years of distance, recession velocity increases by 43.5 miles per second. At some distance, the recession velocity reaches the speed of light. This happens at approximately 14 billion light-years in the current universe. Beyond that, galaxies are receding faster than light. This doesn't violate relativity because they're not moving through space faster than light. Space itself is expanding faster than light can traverse it. Light from those galaxies is emitted in our direction, but the space it must cross is expanding faster than the light can cross it. It's like swimming upstream in a current faster than you can swim. You're making progress through the water, but the water carries you backward faster. The light makes progress through space, but the distance grows faster than the progress. So, the light never arrives. This defines the edge of the observable universe, the cosmological horizon. Objects beyond this horizon are causally disconnected from us. We can never observe them, never interact with them, never receive any information from them. They exist, presumably, but they're forever beyond our reach. And here's the critical point. This horizon is moving inward over time. As the universe continues expanding, and that expansion accelerates due to dark energy, more and more galaxies cross the horizon and disappear from view. Right now, we can see galaxies about 46.5 billion light-years away in any direction. But many of those galaxies are already receding faster than light. We see them only because the light we're receiving left those galaxies billions of years ago, when they were much closer and expansion was slower. The light those galaxies are emitting right now will never reach us, and galaxies currently near the edge of our observable universe will eventually cross the horizon as expansion continues. Let's trace what happens over time. A galaxy currently 10 billion light-years away is receding from us at more than twice the speed of light. We can still see it because we're receiving light, that left it 10 billion years ago, but new light leaving that galaxy now will never reach us. In the far future, even the light we're currently receiving will be so red-shifted, its wavelength stretched so long, that it becomes undetectable. The photons will have so little energy they might as well not exist. And from our perspective, that galaxy fades and disappears. Closer galaxies will take longer, but eventually they too will cross the horizon. The observable universe is shrinking from the outside in. The most distant galaxies disappear first, then slightly closer ones, then closer still. Given enough time, hundreds of billions of years, only our local group remains visible. The Milky Way, Andromeda, and roughly 80 smaller gravitationally bound galaxies. They will eventually merge into a single large elliptical galaxy. Everything else, the Virgo cluster, the Coma cluster, the Fornax cluster, will have been carried beyond the horizon by accelerating expansion. Observers in what remains of our local group will look out and see only their own merged galaxy, maybe a few satellite dwarf galaxies if they remain bound. But everything else will be gone, and the cosmic microwave background will also fade. Right now, the CMB is detectable as microwave radiation at 2.7 Kelvin. But as space expands, this radiation gets redshifted to longer and longer wavelengths and lower energies. Over trillions of years, it will be redshifted into radio waves, then even longer wavelengths. The temperature will drop below 1 Kelvin, below 0.1 Kelvin, approaching absolute zero, asymptotically. Eventually, it will be so diffuse and low energy that it's undetectable with any conceivable technology. The CMB, the most direct evidence we have of the Big Bang, will be erased by expansion. Future civilizations won't be able to observe it. They won't know the universe had a hot, dense beginning. Cosmology as we know it would be impossible. They'd have no way to discover the Big Bang, no way to measure cosmic expansion, no way to infer the universe's history. They'd be observationally isolated, sealed inside a single galaxy with no evidence that anything else ever existed. This has led some physicists to a humbling thought. Are there aspects of cosmology that we already can't access because they've been erased by expansion? Were there structures or events in the very early universe that we have no evidence for because all traces have been redshifted beyond detection? We can observe back to the cosmic microwave background, which formed about 380,000 years after the Big Bang. Before that, the universe was opaque to light, too hot and dense for photons to travel freely. So we have no direct observations of the first 380,000 years. We can infer what happened using physics and theory, but direct observation is impossible. Could there have been interesting structure or events during that time that left no observable traces? We might never know. And similarly, there might be structures or phenomena beyond our current cosmological horizon that we have no way to detect. The observable universe might be a tiny fraction of the total universe. Everything beyond our horizon is unknowable to us, and that sample is shrinking over time as more objects cross the horizon. The universe we can observe is getting smaller, while the total universe continues getting larger. Our window on reality is closing. In this context, we are fortunate to exist now, in an era when the universe is still observable, when distant galaxies are still visible, when the CMB is still detectable, when we can still measure expansion and infer the Big Bang. A few trillion years from now, this won't be possible. Future civilizations will have less information than we do. They'll inherit a lonelier, darker universe, and this raises profound questions about our place in cosmic history. The universe is approximately 13.8 billion years old. Stars will continue forming for at least 100 trillion years, possibly much longer. So we're only about 0.01% of the way through the stellar era. We're incredibly early. Most of the stars that will ever exist haven't formed yet. Most planets haven't formed. Most opportunities for life haven't happened yet. But what we do know is that we exist at a time when the universe is maximally observable. In the deep past, the universe was too hot and dense for structure. In the deep future, it will be too empty and dark for cosmology. Right now, we're in the sweet spot, and that's not entirely coincidence. Life requires certain conditions: stars, planets, stable environments, billions of years of evolution. These conditions exist during the stellar era, so intelligent life, wherever it arises, will tend to find itself in this same window. We observe the universe to be in a life-friendly state because we couldn't exist to observe it otherwise. But even within the stellar era, there's a narrower window for cosmology. Right now we can see distant galaxies and the CMB. In a trillion years, distant galaxies will be gone and the CMB will be undetectable. So there's a brief period, cosmologically speaking, when the universe is both observable and inhabited by intelligence. We're in that period now, and what we're observing is a universe becoming emptier. Let's return to the present and ask, why is the universe empty in the first place? Why isn't space filled with matter? The answer lies in the early universe. In the first moments after the Big Bang, the universe was incredibly dense and hot. All the matter and energy that would eventually form galaxies and stars and planets and us was compressed into an unimaginably small volume. At 1 second after the Big Bang, temperature was approximately 10 billion Kelvin. At 1 millisecond, 1 trillion Kelvin. At 1 microsecond, 10 trillion Kelvin. Go back further and temperatures reach energies where our current physics breaks down entirely. At these temperatures, matter as we know it couldn't exist. No atoms, no molecules, not even protons or neutrons. Just a soup of fundamental particles and energy. Quarks and gluons and electrons and photons, all interacting violently in an incredibly dense plasma. As the universe expanded, it cooled. At about 1 microsecond old, quarks combined to form protons and neutrons. At about 3 minutes, protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium. At about 380,000 years old, the universe cooled enough for electrons to combine with nuclei, forming the first atoms. This moment is called recombination. Before it, the universe was opaque. Photons constantly scattered off free electrons and couldn't travel freely. After recombination, when electrons were bound into atoms, photons could travel freely. The universe became transparent. The photons freed at recombination are what we see today as the cosmic microwave background. They've been traveling through space for 13.8 billion years, redshifted by expansion from visible light into microwaves. The CMB gives us a snapshot of the universe at age 380,000 years, and that snapshot shows the universe was remarkably uniform. Temperature varies by only about 1 part in 100,000. Some regions were slightly hotter and denser than average. Other regions were slightly cooler and less dense. But the variations were tiny. This uniformity is puzzling. How could regions of space billions of light years apart have almost exactly the same temperature? They couldn't have been in thermal contact. Light hasn't had time to travel between them even now, let alone in the early universe. The solution is inflation. Before inflation, the entire observable universe was a tiny region small enough to be in thermal equilibrium, all parts in contact, able to exchange heat, reaching the same temperature. Then inflation stretched this tiny uniform region to enormous size. The uniformity was preserved, stretched out with the space. And inflation also explains why the universe is geometrically flat. Exponential expansion stretches out any initial curvature the same way zooming in on a sphere's surface eventually makes it look flat. But most importantly for our purposes, inflation created the seeds of all structure. The inflaton field was subject to quantum fluctuations. During inflation, these fluctuations were stretched to cosmic scales, a quantum fluctuation smaller than a proton inflated to the size of a galaxy. These stretched fluctuations became the density variations that eventually grew, under gravity, into the galaxies and voids we see today. Now here is the profound connection to emptiness. Dark energy is actively destroying the universe's structure. About 5 billion years ago, dark energy began to dominate. The universe had expanded enough that matter became sufficiently dilute. Dark energy's constant density now contributed more to the total energy density than matter. Expansion began accelerating, and it's been accelerating ever since. In the early universe, matter dominated and gravity was slowing expansion, allowing structures to form. Overdense regions could collapse because expansion wasn't too fast. Matter had time to flow from underdense regions to overdense ones, creating the cosmic web. But now, with dark energy winning, that process is reversing. Objects not gravitationally bound are being pushed apart faster and faster. The cosmic web is being stretched, filaments thinning, voids growing. The universe is evolving toward a state where most matter is concentrated in isolated galaxy clusters separated by voids of almost unimaginable scale. In the far future, over time, scales of hundreds of billions to trillions of years, even gravitationally bound structures may be affected. If dark energy remains constant, its influence grows stronger relative to matter's influence as matter thins out. First, superclusters will dissolve. Then, galaxy clusters. Eventually, in the most extreme scenario called the Big Rip, where dark energy's density increases over time rather than remaining constant, expansion could accelerate enough to tear apart even bound structures. First, galaxy clusters dissolve, then individual galaxies, then stellar systems, then planets, then molecules, then atoms, then atomic nuclei. The universe would be ripped apart at every scale from largest to smallest until nothing remains but isolated particles spreading through infinite space. This is speculative. We don't know if dark energy will remain constant or increase or decrease over time. Current evidence suggests it's at least roughly constant, which means the universe will continue expanding forever, and structures will continue dissolving. The universe's most likely fate is heat death. Not because the universe gets hot, but because it reaches thermal equilibrium, a state where all energy is evenly distributed and no more useful work can be done. Right now, the universe is far from equilibrium. Stars are hot, space is cold, galaxies are dense, voids are empty. These differences allow things to happen. Stars burn, planets orbit, galaxies evolve, life exists. All of it depends on being out of equilibrium, on having energy concentrated in some places and not others. But the second law of thermodynamics says entropy always increases in a closed system. Entropy is a measure of how spread out energy is. The universe started in a low entropy state, with energy concentrated in the Big Bang. As time passes, entropy increases, energy spreads out, differences fade. This continues until everything reaches equilibrium. Maximum entropy, maximum disorder, maximum emptiness in the deepest sense. No concentrated structures remain. Trace this over deep time. For the next 100 trillion years or so, stars will continue forming from gas in galaxies. Not at today's rate, which is already declining, but enough to keep the process going. Small red dwarf stars, the longest-lived type, will keep forming for at least that long. Eventually, gas runs out or becomes too dispersed for new stars to form. By about 100 trillion years from now, star formation will essentially cease. From that point, only existing stars remain, slowly burning out. By about 10 to the power of 15 years, 1 quadrillion years, all stars will have died. No more fusion, no more starlight. The universe enters the degenerate era, containing mostly white dwarfs, neutron stars, and black holes. Everything is dark and cold. Over time, gravitational interactions between objects in galaxies will gradually eject most into intergalactic space. One object speeds up from a gravitational encounter and achieves escape velocity. Another slows down and falls deeper in. Over trillions of years, this process ejects roughly 90% of objects from galaxies. They drift off into intergalactic space, isolated, cooling, never to interact with anything again. The remaining 10% fall toward the galactic center, where they collide, merge, or are captured by the central supermassive black hole. By about 10 to the power of 30 years, galaxies have largely evaporated, and black holes, paradoxically, eventually evaporate too. Stephen Hawking showed in 1974 that quantum effects near a black hole's event horizon cause it to emit radiation. Particle-antiparticle pairs that pop into existence near the horizon can be separated. One falls in, one escapes. From outside, it appears the black hole is emitting particles. This radiation carries away energy, which must come from the black hole's mass. So the black hole slowly loses mass. It evaporates. A black hole with the mass of the Sun takes about 10 to the power of 67 years to evaporate completely. A billion solar mass black hole takes about 10 to the power of 100 years. These are timescales beyond any human intuition. The entire history of the universe to this point is less than a single moment compared to them. But eventually, even the supermassive black holes evaporate. Their final moments are dramatic. As a black hole loses mass, its temperature increases and it radiates faster, accelerating the evaporation. In its last second, a black hole releases as much energy as billions of nuclear bombs. A final flash of gamma rays, then nothing, converted entirely into radiation that spreads into space. By about 10 to the power of 100 years, all black holes have evaporated. What remains? Isolated stellar remnants, cold, dark objects called black dwarfs, drifting through expanding space. Photons redshifted to nearly infinite wavelengths, neutrinos, and dark matter, whatever it is, spread incredibly thin, everything approaching absolute zero. Everything isolated, separated by distances that dwarf even today's intergalactic scales. The observable universe at this point would be a fraction of what it is now. An observer, if any could exist, would see only the immediate local vicinity, perhaps a few nearby black dwarfs within 1,000,000,000 light-years, everything else beyond detection. This is the final state. Heat, death, maximum entropy, complete thermal equilibrium, no differences anywhere, no gradients, no concentrated energy. Nothing can happen because there's no energy differential to power any process. And here's the perspective that matters. From the Big Bang to heat death, the entire era of structure, the era with galaxies and stars and planets and life, is just the first tiny fraction. 10 to the power of 14 years of active star formation, 10 to the power of 30 years of stellar remnants cooling, 10 to the power of 100 years of black hole evaporation, then, effectively forever, in the equilibrium state. The entire history of the universe that we can relate to, everything that has ever happened or will happen that we'd consider significant, occurs in the first 10 to the power of 100 years. After that, just empty space expanding forever. No more events, no more changes, no more history. The universe doesn't so much end as it stops doing anything interesting. The emptiness is the final state, and it will persist forever. Fullness, structure, complexity, all temporary. Emptiness is permanent. But we're not there yet. We live in the stelliferous era, the age of stars. This era began a few 100 million years after the Big Bang, when the first stars formed. It will continue for trillions of years. We're about 0.01% of the way through it, and while the universe is mostly empty now, it's actually in one of its fullest states relative to what came before and what will come after. This moment in cosmic history is uniquely rich, uniquely complex, uniquely full of structure. And here is what makes that remarkable. Consider what had to happen for us to be here. The Big Bang had to occur with exactly the right initial conditions. Inflation had to happen, smoothing the universe and creating quantum fluctuations of exactly the right amplitude. Not so small that structure never forms, not so large that everything collapses directly into black holes. Dark matter had to exist in exactly the right abundance. Dark energy had to exist, but with exactly the right strength, not so strong it prevented structure formation, not absent, or the universe might eventually recollapse. The density of matter had to be precisely right. Stars had to form and evolve, creating heavy elements through nuclear fusion. Those stars had to explode as supernovae, scattering those elements into space. Second-generation stars like the Sun had to form from gas enriched with these heavy elements. Planets had to coalesce from the debris around these stars. At least one planet had to sit in the habitable zone at exactly the right distance from its star for liquid water. That planet needed a stable climate for billions of years while life evolved from chemistry. Life had to survive countless extinction events, asteroid impacts, climate shifts, volcanic eruptions. Evolution had to produce increasingly complex organisms over billions of years. Eventually, intelligence emerged, consciousness capable of abstract thought and scientific inquiry. That intelligence had to develop language, writing, mathematics, science, technology. Civilizations had to arise that valued knowledge and invested resources in understanding the universe. Telescopes had to be built. Every step in this chain could have failed, any of them. Change any one factor significantly, and we might not be here. Some physicists interpret this as evidence for a creator who set the parameters deliberately. Others invoke the multiverse, the idea that there are countless universes with different parameters, and we necessarily find ourselves in one where conditions permit life. Others point out that we're still early in understanding physics, and we might discover deeper principles explaining why parameters have the values they do. All of these perspectives have merit. None are conclusively proven. But regardless of interpretation, the fact remains. We live in a universe that permits complexity and consciousness, and that universe is overwhelmingly empty. The emptiness isn't a bug, it's a feature, a necessary consequence of the conditions that allow structure. Too dense and everything collapses into black holes. Too empty and gravity can't pull matter into galaxies. The universe had to be exactly this empty to produce galaxies and stars and us. And it's getting emptier because dark energy is accelerating expansion, isolating structures from each other. But this process takes trillions of years. We exist in the era when the universe is full enough to observe and study, when there are still galaxies visible in our telescopes, when the CMB is still detectable, when we can still piece together the universe's history and project its future. Eventually, the observable universe will shrink to just our local group. Then eventually, even our own merged galaxy will be the only structure visible. After that, on timescales beyond comprehension, even our galaxy will dissolve as stars burn out and black holes evaporate. Heat death, maximum entropy, maximum emptiness. But that's trillions of years away. For now, we're here. We're conscious. We can observe and understand. We are a temporary pattern in matter and energy, emerging briefly before dissolving back into the void. But while we exist, we can observe, we can measure, we can understand. We can look at the emptiness and calculate why it's empty. We can measure dark matter even though we can't see it. We can detect dark energy even though we don't know what it is. We can trace the universe's history from the Big Bang to the present and project forward to the far future. This ability to comprehend our situation, to grasp the scale and structure and fate of the universe, is perhaps the most remarkable phenomenon in all of nature. Consciousness arising from matter, observing itself, understanding itself, recognizing its own impermanence, and doing so in a universe that is fundamentally, profoundly, terrifyingly empty. We are islands of complexity in an ocean of void, temporary structures in an expanding universe, brief moments of order in a cosmos trending toward disorder. But we're real, we're here, and we understand why. That understanding doesn't change the physics. It doesn't stop the expansion or prevent the heat death, but it transforms the meaning of emptiness. An empty universe that's never observed remains just empty. An empty universe that's observed and comprehended becomes something more. It becomes context, backdrop, the stage on which the drama of existence plays out. And the emptiness itself becomes meaningful because it explains why we are rare, why we are special, why this moment matters. If the universe were full, if galaxies were packed together like grains of sand on a beach, our existence wouldn't be remarkable. But they're not. Galaxies are separated by millions of light years of void. Most of space contains nothing, and that makes the parts that do contain something, the thin filaments where galaxies cluster, the rare places where stars shine and planets orbit, profoundly significant. We exist in the exception, not the rule. In rare pockets of density scattered through boundless emptiness, and we are conscious of that fact. We understand that we are rare, that our existence is improbable, that the emptiness surrounding us is the norm, and we are the exception. We are the universe's way of knowing itself. the rare places where matter organized into structures capable of observation and comprehension, where physics gives rise to chemistry, chemistry to biology, biology to consciousness, consciousness to science, where the universe looks back at itself and understands why it is empty. The universe is empty. Yes, terrifyingly, profoundly, overwhelmingly empty. Almost everything is nothing. Almost all of space is vacuum. The matter that does exist is mostly invisible and mysterious, understood only through its gravitational effects. Dark energy is tearing space apart, accelerating expansion, pushing everything away from everything else. The cosmic web is dissolving. Structures are fading. The lights are going out one by one. Entropy increases. Order decreases. Complexity gives way to simplicity. The universe is running down, cooling off, spreading out, approaching its final equilibrium. But in that small fraction of space that does contain visible matter, in the thin filaments where galaxies cluster, in the rare regions where stars form, in the vanishingly unlikely places where planets orbit at just the right distance for life to arise, something extraordinary happens. Matter organizes itself into increasingly complex forms. Atoms become molecules. Molecules become cells. Cells become organisms. Organisms become conscious. And consciousness looks back at the universe and understands it. We are the universe noticing itself. Brief sparks of consciousness in an ocean of darkness. Temporary patterns in an expanding void. But we are here now, and we understand why the universe is empty. And that understanding, that ability to grasp the terrifying physics of cosmic emptiness while existing as complex structures within it, that's not nothing. That might be everything that matters in this brief moment before